So 5.4 work, right? Um, uh, for some of us haven't taken, physics yet, so I'm gonna give you a little bit background of the physics, and then what we mainly want to look into is like, from what we learned in this chapter 5, how we're gonna look at in terms of the mathematical point of view on like computing the work, okay, of a certain thing. So what is a work? Work is basically like, force time the distance. Like if what is a force? If you have an object, like if you put it on a table, and if you're pushing it or pulling it, so those are the force that you are talking about. Okay, so the very first formula that you're going to learn in physics, right, is F equal to ma, which is force is mass time accelerations. Right, that's the formula for the force. And the work is basically how much energy required for you to move, like the object from one to another place, right? So we're going to talk about like a linear distance point of view. So if you put an object on a table and if you push it from starting point to like 5 feet away, so like how much work is required to move this object to there, right? So that's what we talk about for work, which is work is force time the distance. Right? So that's basically the constant, like, not necessarily all the time your force will be constant and your distance will be like, only a certain point anymore, right? So that's why we want to look at it. So in units wise, for this sessions, we need to know 2 different unit system. One is a international SI metric system, and the other one is a British system, right? Unit system. So mass, we use a kilogram, right? And distance will be the meter, right? And I should put this m as a small one, right? That's the notations for the meter. And then in British system, we'll be using feet and inches. And of course, you can talk about kilometer, centimeter, so on and so forth. You can convert it. This is in the center. The time will be the seconds. And so the accelerations, right, for the SI unit system will be meter per second square. And for the British will be feet per second square and inches per second square. Since the force is a mass times an accelerations, so in SI unit system will be kilogram times, right, meter per second square. So this unit, kilogram times meter per second square, we put it as uppercase N, which is called the Newton unit, right? So that's the new units for the force, right? The Newton units. And for the British system will be the pound is basically the force. And work is basically force times the distance, which is going to be Newton meter, right? That will be basically using a new notations, a new units, which is called joule. Right? But in the British system, it will be just talking about foot pound and inches pound. So those are the units that you need to know, right? And there is a conversions, approximations, like in 1 Newton is approximately 0.225 pound. Right? 1 Newton meter is approximately 0.74 foot-pounds. Right? So the water weight is basically 62.5 pound for cubic feet per cubic feet. So you talk about per volume, right? And that is basically equal to approximately 1,000 kilogram meter per cube, right? Cubic meter. So those are the units that we need to know, right? To some of the problem, and then there's more that you need to know later on, right? So this is basically from physics point of view, right? What is the formula, and then these are the unit system. But in mathematics point of view, what we want to do is when we talk about the force, is basically if a function f is a force representing force, right, at x, and f is a continuous between a and b, then the work done is in moving an object along the x-axis from point A to point B. That will be from integral from a to b of f of x times dx. So that's basically what we are talking about is this, the Riemann sum, right? So if you're looking at, here's an object moving from point A to point B. And we're not going to talk about in mathematics point of view, I mean, we're not going to talk about the whole thing at once. What we're going to do is we're going to basically break it down, right, for every single little part, and then talk about each part and add it up. So that's what basically this integral idea is. So we want to talk about what is the work done, work required to move this little distance, and this little distance, and this little distance, and we are adding up all of these work together to talk about what the entire, right, work that needs to move this object from point A to point B. So that's basically the idea from the point of mathematics point of view. So, you know, to make it easier to formulate it, we're going to be breaking down those, like, you know, little distance equal part, and then try to make it infinitely many of them. So therefore, these little distance will be what? Very, very tiny, right? As n approaches to infinity. So that's the idea that we're going to use, and that's what we're going to try to, you know, break it down in a problem so that it will make it easier for us to set it up from the mathematical point of view on an integral. So is there any questions on this? So a heavy rope 50 feet long, right, weighted to 25 pounds, is hanging over the edge of the building, which is 120 feet height. How much work is done, right, in pulling the ropes to the top of the building? So basically, like, you know, if you pull it up, the first time you pull it up, you know, it's basically what the whole entire rope is down here, right, tangling. So the weight is more. So the work that you need to put is more. And then as you move on and then up, like, you know, the distance will be shorter and shorter, right, to pull it up, because the rope is getting shorter and shorter as we put it in. So what we want to do is first, we want to look at, you know, this whole 50 lengths, right, and try to set it up like, you know, an origins, because based off on how you set it up, the origins, like your starting point, then your distance will be, you know, looking at differently. So you can basically put your, you know, origins at the top of the building, or you can put your origin as what? At the bottom of the building, okay, or bottom of the rope. So based off on this, where you put it down, then the distance that you need to formulate it, right, the expression for the distance will be different from here, right? So we're going to talk about that later on. Very soon. So first thing, the idea that we had is basically what we want to do is, if we are pulling up this rope, right? If we are pulling up this rope, then we want to basically what? Look at each little part. So what we're going to do is we're going to try to break it into, like, you know, equal length, right? That's the idea from what we get from the integral, right? We're going to put it on equal length and try to look at one case. So if I break it into everything in equal lengths on this 50 feet, right, you know, these little portions, we're going to be talking about what? The length delta x, right? The change in basically what? A value. So therefore, the length of a small part of the rope, we're going to talk about that as what? Delta x. That's basically, we may be talking about only this little portions, right? These little portions right here. So next thing, what we want to do is what? We want to talk about what is the weight of this little portions, right? Because the weight is basically talking about what? The force, okay? It's basically like, you know, in terms of, it could interpret it as a force right there. So, but to talk about the weight of this little portion, then what we need to do is first we need to know what is the weight of this, you know, entire rope in per foot. So that's basically, we are talking about, we have what? Basically 25 pounds, right? And then divided by what? The length, which is 50. So that will give me 0.5 pounds per foot. Right? And let me just basically talk about this as foot. So I wanted you to keep track of the unit also, so that way you can see that will make sense to you, okay? What we are trying to do, why we are talking about this. So now, when we talk about the weight of this little small portion, that's basically talking about what is the distance that we have. So 0.5 times with the delta x, okay? So we are only talking about what this portions of what pound foot. So you can see that if I multiply this, the weight per pound foot, right? Weight of the weight per foot of the rope, which is pound foot, times with the delta x, which is the feet, then the foot and foot cancels out. So this will left with what? The unit pounds, which is what? This is the unit for the force, right? So let me stop right here. Is there any questions? Now what we want is we want to find out what this entire, right, rope when you rolling up, right, pulling up. So if you talk about this little distance right here, right, little increments right here, and then if that is this point, then how much, right, distance I need to still pull it up? That's what we want to look at it. So if you're talking about this little portion of the rope pulling up all the way to the top, so from here to the top, you know, how much distance that do we need? So that's also depending on, like I pointed out earlier, like, you know, where you actually like put your origins, right? If your origin is on the top, then it will be expressed differently than the origin is at the bottom. So let's say if I put my origins at the bottom right here, right? So that basically means, right? That basically means I'm already this distance from here to there, right? From this distance, that is basically what? Let's say x units. So if I'm moving this section, this point all the way to the top, right? All the way to the top, that's basically going to become what? The distance that we need to move is what? 50 minus x, right? Because the whole entire rope is only 50. If we are starting from this point to up, then we only need to move what? 50 minus x. So that's basically, you know, putting your origin as in the bottom, and then that from origin to your point will be what? X distance, because this distance will be always changing. So therefore the distance that you need to pull it up always changing. If you put your origin all the way on the top, then these two will flip around. X will be on the top, and then the distance that you need to pull up will be X, and then the, you know, where you are originally where your sector is, that will be 50 minus X. So therefore the distance that we need to pull it up right now, that will become what? 50 minus X. So to move this little, you know, this little part of the rope, small part of the rope, all the way up to the top of the building, the work required will be force, which is 0.5 times delta x, right, times with the distance, which is going to be 50 minus x. So that's basically the work required to pull this little small portion all the way to the top. And what we are interested in is what we are interested in doing all of this all together, every little part all together. So the work required, right, to move this whole entire rope will be considered as integral from, the limit will be from 0 to 50, right, 50 feet of what? All of these portions added up together, which is going to be the force, right, times the distance. So it will be 50 minus x times with 0.5, right? And then delta x is basically what? Dx. So this will become basically the setup for the finding the work of pulling this entire rope all the way to the top of the building. And you can basically integrate to get this numerical value. And don't forget this numerical value. Let me put all the units. This is foot, right? This is work will be what? Foot pounds, right? So that's basically the unit that we have right here on the top, right? So don't forget that your unit at the end will be what? Foot-pounds. Okay, and that's the end of the first example. So a cylinder, right? A cylindrical water tank with the radius 10, right? And this is my radius. That'll be 10, right? Foot. And the height of 30. So that's basically what this whole length is 30. With half filled with water, right? And then how much work is required to pump all the water over the upper rim of the tank. So because of this, basically all of this water is going to be pumped out, right? From the top, this top rim. So I'm going to place my axis like this, right? From 0 to 30. And the water level is halfway, so it'll be what? We have 15 foot right there. Okay. So now, like before, what we're going to do is we're going to be looking at, instead of, a layer, a thin layer of water pumping out, and how much work is required to move that thin layer of the water, right? So that basically talking about, I'm putting out one example as this thin layer right here, okay, right, to pump it out. So that basically tells me the thickness of this layer of water, right, a thin layer of water, that will become what? The dx, right? So that's will be my thickness. So we are looking at this particular thickness right here, right, the thin layer. So I can basically say that this will be delta x, and this is in what? Foot. Right? Now, what we need to do is what? We need to find out what is the weight of this thin layer of water, right? Remember, that weight is basically what? Can be interpreted as what? Force, right? But this time is not as straightforward as the previous example anymore, because we don't know the weight, right? From this shape of the cylindrical, we can only find out the volume of the water. So the weight of the thin layer of water is required to find out what? The volume times the density of the water. Right? So that's something that, you might learn it before. If you haven't learned it yet, you need to know this. That's why I'm writing down this formula for you. Right? If you take chemistries or before, then you might know that from your lab. Okay. So first, we need to know what is the volume of the thin layer of water. Right? So the volume is basically what? The area of a circle right here times with the thickness, that will give me the volume. Right? So which is that is what? Pi times the radius square, right? Times with what? The thickness, delta x. That will be the volume, right? Of this one thin layer. So that basically tells me that will be what? Pi times, and the radius is 10, so it'll be 10 square times with the thickness, which will give me 100 pi times delta x. Remember, this is basically what? My radius is in foot, and then the thickness of the water is also in terms of foot, so that will be what? Foot to the third power, cubic feet. Okay. So now, to find out the weight of this one thin layer of water, right? I'm particularly talking about this point. Then what basically is going to happen is what? This volume, 100 pi delta x, times with, right? Times with the density. So what is the density? And we already know it from the unit that I pointed out before, right? The density is what? 62.5 pound-feet to the third power, okay? So that will be approximately 62.5, right? Pound-feet to the third power. So we are talking about what? Pound-feet to the third power times with feet to the third power So notice that our final after you cancel this out, our final unit is basically what? Pounds, which is the unit for the force, right? So I'm trying to point out the unit is consistent with the formula as well. So let me stop right here. Is there any questions? So the distance required to pump it out is basically, looking at this way. At this point, the thin layer at this point, right? The distance from the origin to that thin layer is x. So therefore, to pump out this thin layer to the top, right, from the top of the rim is basically from this entire distance, which is 30 feet, minus this little distance x, so that I can formulate it 30 minus x, right? So which is what? 30 minus x is the distance that need to pump it out. And not only for this thin layer, if my thin layer is at this point right here, then my x will be only this portion. So therefore, the rest of it is what? 30 minus x anyway. So it's very consistent on this formula. Now I have the force and I have the distance formula. So therefore, the work required to pump out a thin layer of water, right? That thin layer of water can be anywhere. Is basically going to become, multiplying these two together. So when I multiply it, this will be what? 625, no, 6,000, yeah, 6,250, right? Pi delta x, that's the force, times with the distance, which is 30 minus what? X. And remember, this is foot, and this is going to be what? Foot pounds. Right? So that's basically one layer of it. Now, if I want to talk about the whole entire work, then that'll be my work is basically integral from 0 to 30. That's my interval. And force times the distance, which is 30 minus x times with 6,250 pi. My delta x is dx. And if you want your numerical value, integrate, simplify and integrate this. And don't forget the end, it will be what? The foot pound is my unit. Okay, so that's the end of this second example. Any questions?